Hello, it's David. Now the other day I demonstrated this PLCC 68 to DIP64 converter for the CPU socket in the Atari STE, and we discussed how we could basically build the backing plate here required for the plug section of the adapter. And I tried this 3D printed square here and attempted to fit it in, and we tried some different ways to go about it. But it wasn't a particularly successful enterprise. My printer's not very accurate, and it turns out that it was scaling slightly differently in one direction to the other. And you can see there's maybe a little bit of a gap up in this corner here, certainly one here. This side looks basically completely down here, completely isolated. This one and this one aren't too bad. So basically that was a bit awkward and a bit of a pain. So what I've done is I've come up with an alternative. Introducing my spring-loaded PLCC plug backplates. Now the idea of these, still 3D printable, but they have a degree of flex built into them. So you print them slightly too long and you bend them down, still got a few bits of 3D printer filament on there, hot off the printer, and you flex them down to provide pressure to the pins. So I'll put the STL files and the Fusion 360 design files linked at the bottom of this video. And with the Fusion 360 files, there are a set of parameters inside there, and you can change it for a different PLCC size. The key variables are the width of that plate there, which should be basically the length of one row of pins plus maybe ½ millimeter, the length from here to here, which should basically be the distance these two rows of pins are apart, plus maybe 1 or 2 millimeters, and the height, which should basically just be enough to cover the length here of your pin minus the black spacer at the bottom. Now, one is designed to go in one direction, one to go in the other orientation, and the spring-loaded parts, you see, are offset so that they will actually fit. So to load them, all we have to do is to insert one plate against the pins like so, making sure not to have it sat on the black spacer, and then apply even pressure to the opposite plate until it slips in. At this point we can now just slide it down into place. It snaps in quite pleasantly. Oh, maybe I've just slightly overdone that side there. I think it might have got onto the, there we go, just got onto the black spacer. So there we are, we heard that click into place. We just check the alignment, make sure that we're pushing all the pins. They look okay. That one maybe we can just nudge a fraction sideways. There we go. And then rotating it through 90 degrees and repeating the step, but this time with the plate in the inverted position. So we'll apply it there. We can squeeze the center if we don't want to apply the pressure on one end. Let's squeeze the center and it shrinks and it just drops down into place. And then it's just a case again of pushing it down and straightening it up. So does it cover each of the pins? Yes. Perfect. So not even any adjustment required for that. And that will just provide a little bit of back pressure to the pins for when it slots into the PLCC socket, which wants to squeeze it inwards and will, over time, cause these pins to splay into the middle. If we want a higher tension, all we need to do is, or higher pressure I should say, all we need to do is to change that length component in Autodesk Fusion 360, add another millimeter, say, and the degree of flex required to fit it will be higher, and therefore the force it exerts on the pins will be higher. But for now I'm going to be using this and see how well it performs. Perhaps just correct. It looks like it's sitting a bit high. There we go. There we go. And we'll see how well this performs. And hopefully this makes up for a lot of the problems that you have through poor tolerance on the 3D printers. I'll let you know how it gets on.